In this module, we shall learn about the random variables of both discrete and continuous types, about their probability functions and distribution functions. In probability, a random variable can be discrete or continuous with their individual probability distributions, which provides a complete description of random variable or of the population over which the random variable is defined. Apart from studying these probability distributions, it is often necessary to characterize the distribution by a few measures like mean and variance, which summarizes the whole set of data and highlights the important characteristics of the population. This module will focus on the probability and cumulative distributions of random variables and the different measures, which helps in studying the distribution more conveniently. After studying this module, you shall be able to, number 1, know what are random variables. Number 2, understand the difference between discrete and continuous variables. Identify the probability distribution of random variables. Evaluate cumulative frequency through distribution function. Let us begin by understanding the meaning of a random variable. For a given sample space S of some experiment, a random variable is any rule that associates a number with each outcome in S. In mathematical language, a random variable is a function whose domain is the sample space and whose range is the set of real numbers. There are two types of random variables. Number 1, discrete random variable. Number 2, continuous random variable. Following the usual convention in statistics, we denote random variables by uppercase letters and particular values of the random variables by corresponding lowercase letters. Moving on to understanding what is a discrete random variable. A discrete random variable is a random variable which can take only specific values, either finite or countable. Suppose we flip a coin and count the number of heads. The number of heads could be any integer value between 0 and positive infinity. However, it could not be any fractional number between 0 and positive infinity. We could not, for example, get 2.5 heads. Therefore, the number of heads must be a discrete variable. Next, moving on to what is a continuous variable. Continuous variable can take any numerical value in an interval or collection of intervals. A continuous random variable is a set of possible values which consist of an entire interval on a number line characterized by infinitely uncountable values within any interval. Example: suppose the fire department mandates that all the firefighters must weigh between 150 to 250 pounds. The weight of a firefighter would be an example of a continuous variable, since a firefighter's weight could take on any value between 150 and 250 pounds. Next, we have the probability distribution of random variables. The probability distribution of a random variable is the list of all possible outcomes of some experiment and the probability associated with each outcome in a given sample space S. It shows how the total probability 1 is distributed over possible values of an outcome of some experiment. Mathematically, the probability function or the probability distribution of the random variable x assigns a real number to each value xi that can be assumed by the random variable x such that 0 is less than equal to pxi is less than equal to 1 for every event xi. P of s is equal to 1. The symbol p in pxi denotes a function rule according to which probabilities are assigned to each and every event in S. A probability distribution may be represented in tabular form as a graph or in the form of a mathematical function. Further, we shall discuss the discrete probability distribution. The distribution indicating the possible numerical values within the range of a discrete random variable which is related to an experiment and their respective probabilities is called a discrete probability distribution or probability mass function. Discrete probability distribution assigns a probability to each of the possible outcomes x of a random experiment, survey, or procedure of statistical inference. The discrete probability distribution satisfies the following two properties. Probability of x lies between 0 and 1, both inclusive, that is, 0 is less than equal to px is less than equal to 1, sigma px is equal to 1. The different types of discrete probability distributions are binomial distribution, Poisson distribution, geometric distribution, hypergeometric distribution, multinomial distribution, negative binomial distribution. Let us understand it with the help of an example. Suppose you flip a coin 2 times. This simple statistical experiment can have 4 outcomes: HH, HT, TH, TT. Now the random variable x represents the number of heads that result from this experiment. The random variable x can only take the values 0, 1 or 2, so it is discrete random variable. The table represents a discrete probability distribution because it relates each value of a discrete random variable with its probability of occurrence. In this example, we have the probability for all possible outcomes of number of heads. The probability of getting 0 heads is 0.25, of getting 1 head is 0.5, and that of getting 2 heads is 0.25. Let us look at another example. A randomly selected family has 3 children. Find the probability distribution of number of boys in a family. Let x be equal to the number of boys in the family, then x is equal to 0, 1, 2 or 3. The column labeled probability identifies the probability of particular outcome assuming that a boy and a girl are likely independent events. Probability of G is equal to probability of B is equal to 0.5. Also, the possible 3-child families are mutually exclusive outcomes. Thus, the probabilities of the outcome are as follows. X represents the number of boys. Probability for all possible values of x is given here. When x is equal to 0, that is the number of boys is 0, then the possible outcome is G, which is equal to 0.5 into 0.5 into 0.5, which is equal to 0.125. When x is equal to 1, the possible outcome is GGB, which is equal to 0.5 into 0.5 into 0.5, which again is equal to 0.125. When x is equal to 1, the other possible outcome is BGG, which is equal to 0.5 into 0.5 into 0.5, which is equal to 0.125. When x is equal to 1, the next possible outcome is GBG, which again is equal to 0.5 into 0.5 into 0.5 equal to 0.125. When x is equal to 2, the possible outcome is BBG, which is equal to 0.5 into 0.5 into 0.5 equal to 0.125. When x is equal to 2, the possible outcome is BGB, which is again equal to 0.5 into 0.5 into 0.5, which is equal to 0.125. When x is equal to 2, the next possible outcome is GBB, which is equal to 0.5 into 0.5 into 0.5 equal to 0.125. When x is equal to 3, no girls in the house, then the outcome would be B, 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 again equal to 0.5 into 0.5 into 0.5 equal to 0.125. Moving on to probability mass function. Probability mass function Px summarizes the probability that the above discrete random variable x will take on certain values x given by 0, 1, 2, 3, which can be described by a formula as P of x is equal to P of x equal to x. So, P of x equal to 0 is equal to P of g, which is equal to 0.125. P of x is equal to 1 is equal to P of bgg or gbg or ggb equal to P of bgg plus P of gbg plus P of ggb, which is equal to 0.375. P of x equal to 2 is equal to P of bbg or gbb or bgb, which is equal to P of bbg plus P of gbb plus P of bgb, which is equal to 0.375. P of x equal to 3 is equal to P of bbb, which is equal to 0.125. In the above, the probabilities corresponding to the various values of x can be read on the vertical axis. Also in the above histogram, since the numerical outcomes plotted on the horizontal axis are mutually exclusive and exhaustive, the area of the histogram will correspond to unity. Further, we shall discuss cumulative probability distribution. If x is a continuous random variable, then a function fx describing the probabilities of x is called probability distribution function of x or probability density function. The following are the properties of probability density function of x. A. 0 is less than equal to f of x is less than equal to 1. Sum of all the probabilities from minus infinity to plus infinity is 1. That is, integral minus infinity to plus infinity f of x dx is equal to 1. Also, p of x equal to x is equal to 0. That is, the probability at any point is 0. Corollary to equation 1 can be written as probability of a less than equal to x less than equal to b is equal to probability of a less than equal to x less than b is equal to probability of a less than x less than b is equal to probability of a less than x less than equal to b. Equation 2 explains that the probability that x takes on specific value x1 equal to a and x2 equal to b is equal to 0. Also, probability of a less than equal to x less than equal to b is equal to integral a to b f of x dx. Explaining equation 1 and 3 by figure A and figure B. In figure A, probability of x equal to c is equal to 0. In figure B, probability of a less than x less than b is equal to integral a to b f of x dx. Let us look at an example now. Consider the probability density function shown in the graph. Suppose we want to know the probability that the random variable x was less than or equal to m. The probability that x is less than or equal to m is equal to the area under the curve bounded by m and minus infinity as indicated by the shaded area. The shaded area in the graph represents the probability that random variable x is less than or equal to m. This is a cumulative probability. However, the probability that x is exactly equal to m would be 0. A continuous random variable can take on an infinite number of values. The probability that it will be equal to specific value such as m is always 0. The mean of probability distribution is called expected value, which indicates its average or central value. It is a useful summary value, a number of the variable's distribution. Two random variables with the same expected value can have very different distributions. The expected value of a random variable x is symbolized by e of x or mu. The variance of a random variable is a non-negative number which gives an idea of how widely spread the values of the random variable are likely to be. The larger the variance, the more scattered the observations on average. The variance gives an impression of how closely around the expected value the distribution is. It is a measure of the spread of a distribution about its average value. Variance is symbolized by V of x or variance x or sigma square. For a discrete probability distribution, Ex is equal to sigma x px for all values of x. Vx, which is equal to sigma square, is equal to E of x minus Ex whole square, which is further equal to E of x square minus E of x whole square. This is equal to sigma x minus mu whole square into px, where Ex is the expected value and Vx is the variance of the discrete random variable x with probability distribution px. For a continuous probability distribution, Ex is equal to minus infinity to plus infinity x f of x dx. Vx is equal to integral minus infinity to plus infinity x minus mu whole square f of x dx, where Ex is the expected value and Vx is the variance of the continuous random variable x with probability distribution f of x. Let us now look at the theory on variance. Variance has the following properties. Variance x is equal to 0 if and only if x is equal to c, c belonging to R. Variance ax is equal to a square into variance x. Variance x plus c is equal to variance x. Variance x is equal to ex square minus ex whole square. Let us understand it with the help of an example. A certain distribution table is given. Find out the expected value and the variance of x. The probability distribution of x is shown in the table. The probability for all possible values of x is given. The probability of getting x is equal to 0 is 1 by 50 and that of x equal to 1 is 10 by 50 and so on. Solution. Ex is equal to 0 into p of x equal to 0 plus 1 into p of x equal to 1 plus 2 into p of x equal to 2 plus 3 into p of x equal to 3 plus 4 into p of x equal to 4 plus 5 into p of x equal to 5, which is further equal to 0 into 1 by 50 plus 1 into 15 by 50 plus 2 into 10 by 50 plus 3 into 10 by 50 plus 4 into 5 by 50 plus 5 into 9 by 50, which comes out to be equal to 2.6. E of x square is equal to 0 square into p of x equal to 0 plus 1 square into p of x equal to 1 and so on up till plus 5 into p of x equal to 5, which is equal to 9. Variance x is equal to sigma square. This is equal to E of x square minus Ex of whole square, which is equal to 9 minus 2.6 whole square. This is equal to 2.24. That is a measure of variability of x. Let us look at an example of continuous variable. Determine the mean and variance of the probability density function given by f of x is equal to 2e to the power minus 2x for x equal to 0, and it is equal to 0 for x less than equal to 0. Also find the probability that it will take on a value between 1 and 4. Applying the above formulae of mean and variance for a continuous probability distribution, we get, in the case of mean, mu is equal to minus infinity to plus infinity x fx dx, which is further equal to 0 to infinity x 2 into e minus 2x dx, which is equal to 1 by 2. In the case of variance, sigma square is equal to minus infinity to plus infinity x minus mu whole square fx dx, which is further equal to integral 0 to infinity x minus half whole square 2e minus 2x dx, which is equal to 1 by 4. Evaluating the necessary integrals, we get integral 1 to 4 2e minus 2x dx is equal to e to the power minus 2 minus e to the power minus 4. Let us look at another example. The path of the monthly sale of a product is given as f of x is equal to 5 by 4 into 1 minus x square for 0 less than x less than 1. Find the expected value and variance. Variance x is equal to e of x square minus ex whole square, where ex is equal to minus infinity to infinity x fx dx. Ex is equal to 0 to 1 x fx dx, which is equal to integral 0 to 1 x into 5 by 4 into 1 minus x square dx, which is equal to 5 by 16. E of x square is equal to integral 0 to 1 x square fx dx, which is further equal to 0 to 1 x square into 5 by 4 1 minus x square dx. This is equal to 5 by 4 integral 0 to 1 x square dx minus 5 by 4 integral 0 to 1 x4 dx, which is equal to 1 upon 6. Therefore, variance x is equal to e of x square minus ex whole square, which is equal to 1 by 6 minus 5 upon 16 whole square, which is equal to 0.069. Further, moving on to the cumulative distribution function. The distribution function fx, also called the cumulative distribution function CDF or cumulative frequency function, describes the probability that a variable x takes on a value less than or equal to a number x. Fx is thus the probability of values less than x. It has been divided further into two types: discrete probability distribution and continuous probability distribution. The cumulative distribution function CDF of a discrete random variable x is the function fx, which tells you the probability that x is less than or equal to x. Thus, to obtain cumulative distribution of x, we cumulate the probabilities px as x varies over the given range. So, if x has PDF p of x equal to x, we have f of x is equal to p of x less than equal to x, which is equal to sigma px taken over x less than equal to x. Let us understand it with the help of an example. For cumulative probability, we calculate the probability that x is less than or equal to some specified value x. For example, by cumulating the probabilities px of the above example of x, which is equal to number of boys, as x varies over the given range of 0 to 3, we obtain the cumulative probability distribution of x as given below. F of 0 is equal to P of 0, which is equal to 0.125 when x is less than equal to 0. F of 1 is equal to P of 0 plus P of 1, which is equal to 0.125 plus 0.375, which is equal to 0.5 when x is less than equal to 1. F of 2 is equal to P of 0 plus P of 1 plus P of 2, which is equal to 0.875 when x is less than equal to 2. F of 3 is equal to P of 0 plus P of 1 plus P of 2 plus P of 3 equal to 1 when x is less than equal to 3. Let us look at the discrete probability distribution graphically. In the figure, we observe that the cumulative function is discontinuous for each successive value of x. Also, the graph of fx will have a jump at every possible value of x and will be flat between possible values. Such a graph is called a step function. The step function reaches the maximum value of 1 when x is equal to 3. The distribution function of a continuous random variable is related to a continuous probability Px given by capital F of x is equal to small f of x less than equal to x is equal to integral minus infinity to x f of u du for minus infinity less than x less than infinity. So fx when it exists is simply the derivative of the distribution function Px is equal to f dash x. Thus it is evident that fx is equal to df of x upon dx. So the area under fx in the interval x1 x2 represents the probability that the random variable x lies in the interval x1 x2 as shown, and f of a is equal to f of x less than equal to a, which is equal to minus infinity to a f of x dx. Also, probability of x1 less than x less than x2 is equal to f of x2 minus f of x1, which is equal to integral x1 to x2 f of x dx. Let us now look at the properties of cumulative distribution function. Number 1. 0 is less than equal to fx is less than equal to 1 for all x. Number 2. Limit of fx as x tends to minus infinity is equal to 0. 3. Limit of fx as x tends to infinity is equal to 1. Fx is a non-decreasing function of x, so x1 less than x2 implies f of x1 less than equal to f of x2. P of x greater than equal to x is equal to 1 minus f of x. The derivative of fx is the density function fx, which can never be negative.